You may have heard that space is cold at around minus 270 cc, close to absolute zero, and therefore just stepping outside would cause your body to instantly freeze solid like in science fiction movies. But the truth is not in that number, but in how cold actually works. Because space is not an environment full of cold air, but is almost a vacuum, with a density of only a few atoms per cubic centimeter, while the air on Earth has a density of about 10 to the 25 molecules per cubic meter. And according to the principles of thermodynamics that James Clerk Maxwell described back in the 19th century, heat only transfers efficiently when there are collisions between particles. So when there are almost no particles at all, the cold no longer works the way you imagine. And this very misunderstanding hides a much more terrifying truth about the nature of the universe. And to go deeper into that, you need to unravel a fundamental misconception that almost everyone makes, which is that when you say a place is cold or hot, you are unintentionally mixing up two completely different concepts, temperature and heat. While in physics, temperature is simply a measure of the average motion of particles, a concept that has been clearly established in thermodynamics since the 19th century. Whereas heat is the actual energy being transferred between systems, like when you touch a piece of cold metal and feel the heat being drawn out of your body. And on Earth, these two things almost always go together because the air around you has an extremely high density, about 10 to the 25 molecules per cubic meter. Enough to constantly collide and carry thermal energy away very quickly. But in interplanetary space, that density drops to only a few particles per cubic centimeter, billions of times lower. And that completely changes the game, because even when the measured temperature is very low, there is simply not enough matter to actually pull heat out of your body at the rate you imagine. And this is not speculation, but has long been described in the work of James Clerk Maxwell, who pointed out that efficient heat transfer depends on collisions between particles. So when you ask, how cold is space, you are applying the logic of a dense gas environment to an environment that is almost nothing, where there is no convection, almost no conduction, and the only mechanism left is thermal radiation, according to the Stefan Boltzmann law, a slow process that depends on the fourth power of the temperature. And it is at this point, if you have followed this far, that your entire intuition about what we call cold begins to collapse completely. And once you understand that what we call cold in space does not work in the familiar way it does on Earth, we can then clearly see what actually happens when an astronaut steps outside the spacecraft. Because they are not stepping into a uniformly cold environment, as many people imagine, but into an environment of extreme thermal conditions, where two completely opposite states exist at the same time, with one side facing the sun receiving about 1,361 watts per square meter of radiant energy, a figure measured by NASA in Earth orbit since the 1970s during the Apollo missions, while the other side facing the deep darkness of space can continuously lose heat and gradually approach the background temperature of about 2.7 Kelvin, or approximately minus 270.45 cc, a value confirmed after the 1965 discovery by Arno Penzias and Robert Wilson. And this creates a temperature difference that can exceed 300 cc on the very same object, a phenomenon that is almost impossible on Earth, where the dense atmosphere always acts like a giant thermostat to even out temperature differences. That is precisely why, from the time of Apollo 11 through the space shuttle programs in the 1980s and 1990s, engineers were forced to design spacecraft as extremely sophisticated thermal control systems, with multi-layer insulation coatings called multi-layer insulations, consisting of dozens of reflective material layers to reduce absorption and emission of energy, along with large radiators to dissipate excess heat into space, according to the Stefan Boltzmann law, because if a surface absorbs too much energy without being able to radiate it away fast enough, its temperature can rise by hundreds of degrees in a short time, and conversely, if it is in shadow, it can continuously lose heat and drop to dangerous levels for equipment. This is also clearly shown in the design of the A7L spacesuit, used in the Apollo missions from 1969 to 1972, where astronauts like Neil Armstrong and Buzz Aldrin had to rely on a water circulating cooling system called the liquid cooling garment to maintain body temperature around 37 Celsius. Because when standing in direct sunlight on the lunar surface, where there is no atmosphere to filter radiation, the environmental temperature can reach about plus 127 Celsius, according to NASA measurements during the Apollo missions. And without this active cooling system, the human body could overheat in just a few minutes due to continuous energy absorption, while at the same time parts of the equipment in shadow could drop below minus 150 cc, causing metals to contract, materials to become more brittle, and electronic components to stop working. Even in modern times, on the International Space Station, which orbits Earth at an altitude of about 400 kilometers with a cycle of about 90 minutes, engineers still have to solve this same basic thermal problem, as the ISS continuously experiences about 45 minutes of sunlight and 45 minutes of darkness in each orbit, and to maintain a stable living environment of about 20 to 25 cc for the astronauts. The active thermal control system uses radiators dozens of meters long to radiate heat into space, while also having electric heaters to keep warm the areas not receiving sunlight, because even a brief energy imbalance can cause the internal temperature to deviate from safe levels. This reality shows that in space, you are never in a fixed temperature, but always exist in a dynamic energy balance state, where every second you are both receiving and emitting energy through radiations. And if these two energy flows are not balanced, your temperature will change continuously over time. And this is the key point I want you to grasp, which is that the biggest problem with space is not cold in the simple sense you think, but the extreme thermal imbalance in an environment that completely lacks the natural mechanisms to regulate it. Because on Earth, the atmosphere, oceans, and convection currents continuously redistribute thermal energy, while in space, there is nothing doing that for you. This turns every spacecraft, every spacesuit, and every living body into a self-sustaining energy balance system, where even a small deviation in design or operation can lead to serious consequences. And when you look at the problem this way, you begin to understand that the cold of space is not frightening because of how low it is, but because it exists in an environment where all thermal stability must be artificially created, and any failure to maintain that balance can quickly turn a habitable environment into a completely uninhabitable one. So how does heat really move? Because in physics, heat is not something vague. It always goes from one place to another, according to very specific mechanisms. And if you do not understand those mechanisms, you will always misunderstand what you are feeling. There are three main ways heat is transferred in nature, and you have lived your whole life with all three, without almost realizing it. The first is conduction, which is when molecules collide directly with each other and transfer energy through those collisions, like when you place your hand on a piece of cold metal in a laboratory and you see heat leaving your hand very quickly, not because the metal is colder in some mysterious sense, but because the free electrons in the metal allow energy to be transferred extremely efficiently, much faster than wood or plastic. And that is why at the same temperature, metal always feels colder. This is not a feeling. This is physics. The second is convection, and this is what you feel most clearly in everyday life, when air or liquid moves and carries heat along with it. For example, when you stand outside on a windy day, the temperature may be only 0 cc, but you feel much colder because the cold air continuously moves across your skin, taking heat away faster, an effect that meteorologists at the National Weather Service call wind chill. And they can calculate this heat loss precisely using models based on wind speed and ambient temperature. And then there is the third mechanism, radiation, where energy is emitted in the form of electromagnetic waves without needing any material medium. And this is the only one of the three mechanisms that can work in a vacuum, beautifully described by the Stefan Boltzmann law from the 19th century, which states that the radiative power of an object is proportional to the fourth power of its absolute temperature, meaning if you double the temperature on the Kelvin scale, the emitted energy increases by 16 times, and this may sound impressive, but it is still much slower than putting your hand in cold water or standing in strong wind. Now, the important thing you need to realize is that on Earth, these three mechanisms always work at the same time. They overlap and create the feeling of cold that you have been familiar with your whole life. When you stand outside in the cold, the air carries heat away through convection. The surfaces you touch take heat through conduction, and your body also radiates to the environment, all at once, and you do not distinguish them. You just call it all cold. But when you step out into space, two of these three mechanisms almost completely disappear. There is no air for convection, not enough matter for conduction, and suddenly you are left with only one mechanism, which is radiation, and this completely changes the game. Space does not have a cold wind blowing through you. There is no material environment actively pulling heat from your body. All that happens is your body emits energy in the form of infrared photons, and the speed of that process is limited by your own temperature and surface area. Nothing else helps accelerate it. If you put numbers to it, a human body at about 37 some P, or about 310 Kelvin, will radiate energy at around a few hundred watts, depending on the surface area and emissivity of skin and clothing. And that means you are losing heat, but not in the violent way you imagine from movies. You will not freeze in a few seconds, because there is no mechanism fast enough to pull heat out of you at that rate. And this is where everything becomes interesting in the way I always like, because your intuition says space is very cold, so I will lose heat very quickly. But physics says the opposite, that you lose heat much more slowly than when standing in cold, windy air on Earth. And that does not mean space is safe. Absolutely not. It just means you have been asking the wrong question from the very beginning, because you were asking how cold is it, while the right question must be how is heat transferred in this environment. When you switch to the right question, everything starts to fall into place very clearly. You realize that the cold in space is not a force attacking you, but the absence of the familiar mechanisms you rely on to understand heat. No convection, no conduction, only radiation, and radiation follows very specific rules, indifferent to your feelings. And this is why space engineers do not talk about keeping warm the way you think. They talk about energy balance, about how many watts a system receives and how many watts it emits, because in space, that is the real language of cold. Once you understand that in space only radiation remains as the sole heat transfer mechanism, we can return to one of the most common mistaken images that you have seen repeated in science fiction movies for many decades, which is the idea that if you step out into space, you will instantly freeze solid like a block of ice in just a few seconds, an almost immediate reaction, as if the cold is an active force attacking you. But when you put that assumption under the light of physics, it no longer holds up, because the human body does not lose heat in such a fast way in a vacuum. In reality, if you start with the basic numbers, a human body at a temperature of about 37 false T, or about 310 Kelvin, will radiate energy according to the Stefan-Boltzmann law with a power of only a few hundred watts, typically in the range of 400 to 600 watts, depending on the surface area and environmental conditions. And if you compare that number with the amount of heat the body contains, you will see that lowering the body temperature to the freezing point cannot happen in a few seconds, but requires a much longer period of time, possibly measured in tens of minutes to hours, under ideal conditions with no additional heat sources. In addition to radiation, the body also loses heat through the evaporation process, especially when pressure drops suddenly in a vacuum, a phenomenon called ebulism, where water in the soft tissues begins to boil at a lower temperature due to the reduced pressure. And this has been documented in NASA vacuum tests from the 1960s, when they were preparing for the Apollo missions, in which scientists observed that water on the surface of the body could evaporate quickly, creating an additional cooling effect. But even when combining both radiation and evaporation, the rate of heat loss is still not enough to cause instant freezing as you see on screen. In reality, physiological models and NASA experiments show that in complete vacuum conditions, the human body can take hours to freeze completely if there is no other heat source, and this is completely contrary to popular intuition. But that does not mean you can survive in space for that period of time, because the real problem is not the temperature, but the lack of oxygen and pressure. When you are exposed to vacuum, the surrounding pressure drops to nearly zero, and the oxygen in the lungs and blood is no longer maintained, leading to brain hypoxia. And according to NASA physiological studies, a person will lose consciousness in only about 10 to 15 seconds, a figure that has been confirmed in real incidents, such as the 1965 vacuum chamber accident at the Johnson Space Center, where a technician was suddenly decompressed and lost consciousness within seconds before being rescued. At the same time, gases in the lungs and body cavities expand as pressure drops, which can cause injury if the person does not exhale in time. And the embolism phenomenon causes water in the tissues to begin boiling, causing temporary swelling. But remarkably, the human skin is elastic enough to withstand this phenomenon for a short time without rupturing, something that has been recorded in space physiology studies. And while all of this is happening, unfiltered solar radiation continues to affect the body, especially UV rays and high-energy particles. But these factors usually require a longer time to cause serious damage, and once again they occur before the cold has time to become the deciding factor. And this is the point where I want you to stop and really think, because it completely reverses the way you have imagined space throughout your life. Space is not a place so cold that it kills you instantly, but a place where your heat loss mechanism becomes slow and limited, while other dangers such as vacuum and lack of oxygen arrive much faster. This does not make space less dangerous, but on the contrary, it makes it more incomprehensible, because you cannot rely on your intuition to predict what will happen. You must rely on physics, and physics tells you that the cold in space is not an active agent, but the result of a system where energy is not exchanged in the way you are familiar with. To understand what really makes this environment dangerous, and it is not the low temperature, but the fact that there is no thermal buffer layer to protect you, because on Earth you are always surrounded by an atmosphere layer about 100 kilometers thick, a giant system that works like a natural thermostat, where air absorbs, retains and distributes heat through convection and conduction, making temperature changes occur slowly and predictably. Even when you move from sunlight into shade, the difference you feel is still softened by the surrounding air layer. But in space, this buffer completely disappears, and you are placed directly into an environment where nothing stands between you and the energy source. No air to carry heat away, no convection currents to even out the differences, no natural mechanisms to soften the thermal changes, and this completely changes the way temperature behaves. When an object in space moves from a sunlit area to a shadowed area, the change is no longer gradual, but can occur very quickly, because there is nothing to slow down that process. And this is not theory, but something that has been directly measured. When NASA observed that surfaces of spacecraft in low Earth orbit can experience temperature changes of up to hundreds of degrees C in just a few minutes when rotating from the illuminated side to the side in the planet's shadow. For example, a surface can be at more than plus 120 C when facing the sun, and then drop below minus 100 C when turning into shadow. And the entire process can take place in a time shorter than 10 minutes, depending on the orbit and material properties, something that is almost impossible on Earth, where air always works to balance the thermal differences. That is precisely why in spacecraft design, engineers never think only about protecting against cold or heat separately. They must design for both conditions at the same time, because the same surface may have to endure both states in a very short cycle, and this requires materials that can withstand continuous expansion and contraction without cracking, thermal systems that can respond quickly to energy changes, and the entire structure must be calculated to avoid heat buildup on one side while the other loses heat too quickly. And this is exactly the point where you begin to see the fundamental difference between Earth and space. On Earth, the environment does most of the regulating work for you, while in space there is nothing doing that at all. Everything must be actively controlled, otherwise the system will quickly become unstable. This also explains why spacecraft are often covered with reflective white or silver material to reduce energy absorption from the sun, and at the same time have radiators to radiate excess heat outward, because without these mechanisms, heat can accumulate to the point of destroying equipment, while other parts of the ship can become too cold to operate. And when you look at this from a physics perspective, you begin to see that space is not a simply cold environment, but an environment where thermal stability does not exist at all, where every object is continuously pushed out of equilibrium and must find its own way back to that state through design and engineering. And this is what makes space truly dangerous, not because of how cold it is, but because it provides no natural mechanisms to protect you from extreme thermal fluctuations. And if you do not understand this, you will continue to think of space as a simply freezing place, while in reality it is a dynamic, harsh, and completely unforgiving environment, where every small change in energy balance can lead to major consequences, and where life can only exist if you have the ability to control heat precisely down to every watt. Once you have seen that space has no thermal buffer layer to soften energy changes, the next step is to understand that even sunlight is no longer like what you are used to on Earth. Because on the surface of this planet, sunlight has been significantly reduced as it passes through the atmosphere. About 25% to 30% of the energy is reflected or absorbed by clouds, dust and gas molecules. And in addition, the ozone layer filters out most of the dangerous ultraviolet rays, making the energy you actually receive when standing in the sun usually only around 1001 under good conditions. But when you leave the atmosphere and enter space, you face directly what physicists call the solar constant, about 11361 a figure that NASA has accurately measured over many decades from satellites and missions like Nimbus and orbital observation stations. And this means you are receiving significantly more energy than when standing on the ground, with no clouds to block it, no air to scatter it, no ozone to filter high energy radiation. And this is not just a difference in numbers, it is a difference in nature, because when energy arrives directly without being reduced, exposed surfaces can heat up very quickly, especially metals or materials with high absorption. And in an environment with no convection to carry heat away, heat accumulates right at that surface, causing the temperature to rise by hundreds of degrees C in a short time, a phenomenon that has been recorded in tests and space missions from the 1960s. That is precisely why, in the Apollo program from 1969 to 1972, NASA engineers had to design special reflective coatings, often white or silver, to reduce the amount of energy absorbed from the sun, and at the same time optimize the ability to emit heat outward. Because if a surface absorbs too much energy without being able to emit it fast enough, heat will accumulate to the point of destroying the material structure or damaging the internal systems. This applies not only to spacecraft, but also to equipment and spacesuits, where every surface must be carefully calculated to balance absorption and emission of energy, because even a small deviation can cause the temperature to exceed safe limits in a very short time. And if you remove all these protective layers, if you imagine a bare object directly under sunlight in space, you will see that it does not just avoid freezing, but on the contrary, it can heat up quickly to an extremely dangerous level, while at the same time, the part in shadow continues to lose heat and become deeply cold, creating a contrast that you almost never experience on Earth. And this is the point where everything starts to become truly counterintuitive. Because space is not a place that is only cold. It is an environment where hot and cold exist simultaneously, where you can be heated on one side and frozen on the other. And all of this happens not because there is some cold source, but because there is no mechanism to redistribute energy. And when you look at this from a physics perspective, you begin to see that sunlight in space is not only stronger, but also dangerous in a very specific way, because it is not controlled by any buffer layer. And that means every system must take complete responsibility for handling the energy it receives. And this is precisely why space engineers always say that the problem is not whether space is cold or hot, but that you are in an environment where energy arrives directly and leaves directly, with no intermediary, no filter, no mercy. And if you do not design your system to deal with that, it will fail very quickly. And when you put all of this together, you begin to see clearly that what is scary in the title is not in the low temperature number, but in the reality that space can simultaneously be extremely cold and extremely hot, an environment where all your intuitions about heat no longer hold true. Once you understand that in space only radiation remains as the sole heat transfer mechanism, we can return to one of the most common mistaken images that you have seen repeated in science fiction movies for many decades, which is the idea that if you step out into space, you will instantly freeze solid, like a block of ice, in just a few seconds, an almost immediate reaction, as if the cold is an active force attacking you. But when you put that assumption under the light of physics, it no longer holds up, because the human body does not lose heat in such a fast way in a vacuum. In reality, if you start with the basic numbers, a human body at a temperature of about 37 Celsius, or about 310 Kelvin, will radiate energy according to the Stefan-Boltzmann law, with a power of only a few hundred watts, typically in the range of 400 to 600 watts, depending on the surface area and environmental conditions. And if you compare that number with the amount of heat the body contains, you will see that lowering the body temperature to the freezing point cannot happen in a few seconds, but requires a much longer period of time, possibly measured in tens of minutes to hours, under ideal conditions with no additional heat sources. In addition to radiation, the body also loses heat through the evaporation process, especially when pressure drops suddenly in a vacuum, a phenomenon called ebullition, where water in the soft tissues begins to boil at a lower temperature due to the reduced pressure. And this has been documented in NASA vacuum tests from the 1960s, when they were preparing for the Apollo missions, in which scientists observed that water on the surface of the body could evaporate quickly, creating an additional cooling effect. But even when combining both radiation and evaporation, the rate of heat loss is still not enough to cause instant freezing as you see on screen. In reality, physiological models and NASA experiments show that in complete vacuum conditions, the human body can take hours to freeze completely if there is no other heat source. And this is completely contrary to popular intuition. But that does not mean you can survive in space for that period of time, because the real problem is not the temperature, but the lack of oxygen and pressure. When you are exposed to vacuum, the surrounding pressure drops to nearly zero, and the oxygen in the lungs and blood is no longer maintained, leading to brain hypoxia. And according to NASA physiological studies, a person will lose consciousness in only about 10 to 15 seconds, a figure that has been confirmed in real incidents, such as the 1965 vacuum chamber accident at the Johnson Space Center, where a technician was suddenly decompressed and lost consciousness within seconds before being rescued. At the same time, gases in the lungs and body cavities expand as pressure drops, which can cause injury if the person does not exhale in time. And the ebullition phenomenon causes water in the tissues to begin boiling, causing temporary swelling. But remarkably, the human skin is elastic enough to withstand this phenomenon for a short time, without rupturing, something that has been recorded in space physiology studies. And while all of this is happening, unfiltered solar radiation continues to affect the body, especially UV rays and high-energy particles. But these factors usually require a longer time to cause serious damage. And once again, they occur before the cold has time to become the deciding factor. And this is the point where I want you to stop and really think, because it completely reverses the way you have imagined space throughout your life. Space is not a place so cold that it kills you instantly, but a place where your heat loss mechanism becomes slow and limited, while other dangers such as vacuum and lack of oxygen arrive much faster. This does not make space less dangerous, but on the contrary, it makes it more incomprehensible, because you cannot rely on your intuition to predict what will happen. You must rely on physics, and physics tells you that the cold in space is not an active agent, but the result of a system where energy is not exchanged in the way you are familiar with. To understand what really makes this environment dangerous, and it is not the low temperature, but the fact that there is no thermal buffer layer to protect you, because on Earth, you are always surrounded by an atmosphere layer about 100 kilometer thick, a giant system that works like a natural thermostat, where air absorbs, retains and distributes heat through convection and conduction, making temperature changes occur slowly and predictably. Even when you move from sunlight into shade, the difference you feel is still softened by the surrounding air layer. But in space, this buffer completely disappears, and you are placed directly into an environment where nothing stands between you and the energy source. No air to carry heat away, no convection currents to even out the differences, no natural mechanisms to soften the thermal changes. And this completely changes the way temperature behaves. When an object in space moves from a sunlit area to a shadowed area, the change is no longer gradual, but can occur very quickly, because there is nothing to slow down that process. And this is not theory, but something that has been directly measured. When NASA observed that surfaces of spacecraft in low Earth orbit can experience temperature changes of up to hundreds of degrees C in just a few minutes, when rotating from the illuminated side to the side in the planet's shadow. For example, a surface can be at more than plus 120 capta C when facing the sun, and then drop below minus 100 capta C when turning into shadow. And the entire process can take place in a time shorter than 10 minutes, depending on the orbit and material properties, something that is almost impossible on Earth, where air always works to balance the thermal differences. That is precisely why in spacecraft design, engineers never think only about protecting against cold or heat separately. They must design for both conditions at the same time, because the same surface may have to endure both states in a very short cycle, and this requires materials that can withstand continuous expansion and contraction without cracking, thermal systems that can respond quickly to energy changes, and the entire structure must be calculated to avoid heat buildup on one side while the other loses heat too quickly. And this is exactly the point where you begin to see the fundamental difference between Earth and space. On Earth, the environment does most of the regulating work for you, while in space there is nothing doing that at all. Everything must be actively controlled. Otherwise, the system will quickly become unstable. This also explains why spacecraft are often covered with reflective white or silver material to reduce energy absorption from the sun, and at the same time have radiators to radiate excess heat outward, because without these mechanisms, heat can accumulate to the point of destroying equipment, while other parts of the ship can become too cold to operate. And when you look at this from a physics perspective, you begin to see that space is not a simply cold environment, but an environment where thermal stability does not exist at all, where every object is continuously pushed out of equilibrium and must find its own way back to that state through design and engineering. And this is what makes space truly dangerous, not because of how cold it is, but because it provides no natural mechanisms to protect you from extreme thermal fluctuations. And if you do not understand this, you will continue to think of space as a simply freezing place, while in reality it is a dynamic, harsh, and completely unforgiving environment, where every small change in energy balance can lead to major consequences, and where life can only exist if you have the ability to control heat precisely down to every watt. Once you have seen that space has no thermal buffer layer to soften energy changes, the next step is to understand that even sunlight is no longer like what you are used to on Earth, because on the surface of this planet, sunlight has been significantly reduced as it passes through the atmosphere. About 25% to 30% of the energy is reflected or absorbed by clouds, dust, and gas molecules. And in addition, the ozone layer filters out most of the dangerous ultraviolet rays, making the energy you actually receive when standing in the sun usually only around 1,000 Wb/m was under good conditions. But when you leave the atmosphere and enter space, you face directly what physicists call the solar constant, about 1,1361 Wb/m, a figure that NASA has accurately measured over many decades, from satellites and missions like Nimbus and orbital observation stations. And this means you are receiving significantly more energy than when standing on the ground, with no clouds to block it, no air to scatter it, no ozone to filter high-energy radiation. And this is not just a difference in numbers, it is a difference in nature, because when energy arrives directly without being reduced, exposed surfaces can heat up very quickly, especially metals or materials with high absorption, and in an environment with no convection to carry heat away, heat accumulates right at that surface, causing the temperature to rise by hundreds of degrees C in a short time, a phenomenon that has been recorded in tests and space missions from the 1960s. That is precisely why in the Apollo program from 1969 to 1972, NASA engineers had to design special reflective coatings, often white or silver, to reduce the amount of energy absorbed from the sun, and at the same time optimize the ability to emit heat outward, because if a surface absorbs too much energy without being able to emit it fast enough, heat will accumulate to the point of destroying the material structure or damaging the internal systems. This applies not only to spacecraft, but also to equipment and spacesuits, where every surface must be carefully calculated to balance absorption and emission of energy, because even a small deviation can cause the temperature to exceed safe limits in a very short time. And if you remove all these protective layers, if you imagine a bare object directly under sunlight in space, you will see that it does not just avoid freezing, but on the contrary, it can heat up quickly to an extremely dangerous level, while at the same time, the part in shadow continues to lose heat and become deeply cold, creating a contrast that you almost never experience on Earth. And this is the point where everything starts to become truly counterintuitive, because space is not a place that is only cold. It is an environment where hot and cold exist simultaneously, where you can be heated on one side and frozen on the other. And all of this happens not because there is some cold source, but because there is no mechanism to redistribute energy. And when you look at this from a physics perspective, you begin to see that sunlight in space is not only stronger, but also dangerous in a very specific way, because it is not controlled by any buffer layer. And that means every system must take complete responsibility for handling the energy it receives. And this is precisely why space engineers always say that the problem is not whether space is cold or hot, but that you are in an environment where energy arrives directly and leaves directly, with no intermediary, no filter, no mercy. And if you do not design your system to deal with that, it will fail very quickly. And when you put all of this together, you begin to see clearly that what is scary in the title is not in the low temperature number, but in the reality that space can simultaneously be extremely cold and extremely hot, an environment where all your intuitions about heat no longer hold true. And if you want to see that everything we have just discussed is not only theory but measurable reality, then you do not need to look any further than the moon, because it is a perfect natural experiment on how heat works in a near vacuum environment, where there is almost no significant atmosphere to interfere with heat transfer, no air for convection, no buffer layer to distribute energy, and this makes it an almost ideal model of the space environment we are trying to understand. When the moon's surface faces the sun, it receives direct radiation of about 1361 Wolpussu, just like any object in space near Earth. And because there is no atmosphere to reflect or absorb energy, the surface temperature can rise to about plus 127 Celsius, a figure that was directly measured during NASA's Apollo missions from 1969 to 1972, where heat-sensing instruments were placed on the surface and sent data back to Earth, showing how quickly and intensely heat buildup occurs when there is no regulating mechanism at all. But the real interesting part is not on the sunlit side, but on the dark side. Because when the moon rotates out of sunlight and enters its long night, which lasts about 14 Earth days, due to the synchronous rotation cycle totaling 29.5 days, the surface no longer receives energy from the sun, and because there is no air to retain heat, no oceans to store energy, no clouds to reflect radiation, all the previously accumulated heat begins to escape into space as radiation, causing the temperature to drop to about minus 173 Celsius. And in some deep crater regions that never receive sunlight, the temperature can even drop below minus 200 Celsius. This creates a temperature difference of nearly 300 Celsius between day and night, a level of variation that you can almost not imagine if you only rely on Earth experience, where the difference between day and night is usually only a few dozen degrees, because the atmosphere and oceans continuously regulate heat. And what is important here is not just the numbers, but the cause of them, because this harshness does not come from the moon being in a cold environment, but from its complete lack of a system to hold and distribute heat, meaning every point on the surface essentially operates independently, heating up when it receives energy and cooling down when it loses energy, with no mechanism to even out that difference. This is exactly what astronauts in missions like Apollo 11, Apollo 12, and Apollo 17 had to face, when they not only had to protect themselves from vacuum, but also had to deal with extreme thermal changes between light and shadow. And that is why every piece of equipment they carried, from spacesuits to measuring instruments, had to be designed with extremely precise thermal control systems. And when you look at the moon this way, you begin to see clearly that it is not just a celestial body near Earth, but a giant laboratory for thermal physics in vacuum, where everything happens exactly as the laws predict, with no shielding, no buffer, no mercy. And this leads us to a very important conclusion, which is that space does not have a stable temperature as you think. It is not an environment with a single number you can assign to it, but a system where temperature depends entirely on the energy balance at each point, at each moment, and when there is no atmosphere to regulate it, that balance can change extremely. And when you combine this with what we have said before, you begin to see that the cold of space is not something simple, but the manifestation of an environment where every object is forced to handle its own energy. And if it cannot do that, it will quickly fall into one of two extreme states, either too hot or too cold. And that is exactly what makes space one of the harshest environments we have ever known. Not because it is only cold, but because it is unstable in any way you are familiar with. And when looking at the moon as a natural laboratory where temperature can fluctuate by nearly 300 Cs, simply because of the lack of atmosphere, you will begin to understand why everything humans bring into space must be designed in a completely different way. And one of the clearest examples is the spacesuit. Because if you still think that a spacesuit exists mainly to keep warm, then you are missing the most important part of the story. The Apollo A7L spacesuit, used in missions from 1969 to 1972, is not just a shell to protect from vacuum and provide oxygen, but an extremely sophisticated thermal control system, designed based on very precise thermodynamic principles. Because the problem that astronauts like Neil Armstrong or Gene Cernan faced was not instant freezing, but thermal imbalance that could push their bodies into an overheated state in a short time. When you stand on the lunar surface in direct sunlight, where the temperature can reach about plus 127 degrees, you have no atmosphere to filter radiation or carry heat away, and your body, which always maintains about 37 degrees, continuously generates heat through metabolism, usually around 100 watts at rest, and can rise to several hundred watts when active. And all this heat, plus the energy absorbed from the sun, must be removed efficiently. Otherwise, body temperature will rise quickly to dangerous levels. That is why inside the A7L suit, there is a layer called the liquid cooling garment, a system consisting of hundreds of small tubes carrying water that run throughout the astronaut's body, where water is pumped in circulation to absorb heat from the skin and then carry it to the suit's heat exchanger system, where this energy is radiated out into space, a process that has been carefully calculated to ensure balance between generated heat and removed heat. This means the spacesuit is not just a passive insulating layer, but an active environmental control system, a kind of personal air conditioner that works in a vacuum environment where there is no air to help you cool down. And if you remove this system, if you keep only the insulating layers without a heat dissipation mechanism, you will not freeze, you will overheat, because energy cannot escape fast enough. And this is something many people never think about when they imagine space. At the same time, the suit must also handle the opposite side of the problem. When the astronaut moves into shadow, where the temperature can drop below minus 150 Celsius, and at that point the system must reduce the heat dissipation rate, or even provide supplemental heat to keep the body stable. And this is done by adjusting the water flow, multi-layer insulation, and carefully arranged reflective materials. All of this shows that in space, you are never in one temperature. You are always in a dynamic energy balance system, where every watt of energy in and out must be controlled. And if that balance is broken, the consequences come very quickly. This is also why NASA engineers do not talk about designing to protect against cold or heat separately. They talk about thermal control, meaning overall heat management, because in the space environment, these two concepts cannot be separated. You always have to address both at the same time. And when you look at the spacesuit this way, you begin to see that it is not a simple protective garment, but a complete life support system, a device that maintains thermal balance in an environment that has no natural mechanisms to do it for you. And this leads us to a very important conclusion, which is that the main problem in space is not cold in the sense you think, but maintaining thermal stability in a completely unstable environment, and the spacesuit is the clearest proof of that. A system designed not only to keep you alive, but to keep you in a fragile energy balance that, without it, the human body simply cannot exist. If you want to see that same principle expanded to a much larger scale, look at the International Space Station, because this is no longer a suit for one person, but an entire system more than 100 meters long, weighing more than 400 tons, operating continuously in space, and the entire structure is essentially a giant heat management machine. The ISS orbits Earth at an altitude of about 400 kilometers, with a speed of about 7.66 kilometers per second, completing one orbit in only about 90 minutes. And that means every 45 minutes, it switches from direct sunlight to complete darkness behind Earth, an extreme thermal cycle that repeats about 16 times each day. In each such cycle, the station's surfaces can be heated when facing the sun and immediately afterward lose heat rapidly when entering shadow, and with no atmosphere to soften the process. Everything must be controlled actively and precisely. NASA and its international partners designed for the ISS a system called the Active Thermal Control System, in which coolants like liquid ammonia are pumped in circulation through hundreds of meters of tubing to absorb heat from electronic equipment, computers, life support systems, and heat generated by the astronauts' bodies then carry this heat to huge radiators mounted outside the station. These radiators have a very large area, stretching dozens of meters, and they work by radiating heat into space, according to the Stefan-Boltzmann law, because that is the only mechanism left to remove energy. At the same time, on the opposite side of the equation, when the station enters shadow and surfaces begin to lose heat, electric heaters are activated to keep equipment from freezing, because many electronic components and fluid systems only operate stably within a certain temperature range, and if the temperature drops too low, they can stop working or suffer permanent damage. Inside the station, the environment must be maintained at about 20 to 25 degrees, close to living conditions on Earth, to ensure astronauts can work and live normally during missions lasting months. And to achieve that, the thermal system must continuously adjust, responding to energy changes from the sun, from equipment, and from human activity. What is important here is that the ISS is not in one fixed temperature. It is always in a dynamic energy balance state, where every second, kilowatts of energy are absorbed and emitted, and the entire system must keep these two energy flows balanced with very small error. This is not a minor detail in the design, but one of the greatest challenges of space engineering, because if the heat dissipation system works inefficiently, heat can accumulate and damage equipment, while if too much heat is lost, critical systems can freeze. In fact, during the operational history of the ISS, since the first module was launched in 1998, there have been many times when thermal control systems had to be repaired or adjusted, because even a small failure in thermal balance could affect the entire station. And when you look at such a complex structure operating continuously in a harsh environment, you begin to see clearly that the problem of space is not cold in the simple sense, but that you must continuously manage energy in an environment that has no natural mechanisms to help you do so. This also comes back to the spacesuit we just discussed, only different in scale, because whether it is a human or a giant space station, the principle remains the same. You must maintain balance between energy in and energy out. And if you cannot do that, the system will quickly fall into a state where it cannot exist. If you push this story a little further, out beyond Earth orbit, and out of the region where the International Space Station is operating, you will begin to see a much more profound change, because up to this point, everything we have talked about is still happening in an environment that is relatively close to the sun, where the main energy source still exists and still dominates most of the thermal balance. But when you begin to move away from the sun, you are not only moving away from the light, but you are moving away from the entire main energy supply of the solar system. And that is when everything starts to change in a way that your intuition can almost not keep up with. At Earth's distance, as we have said, solar radiation energy is about 11361 Waldie-Mertapsurid. But when you go farther, this energy decreases with the square of the distance, a very basic law of physics described by the inverse square law, meaning if you go twice as far, the energy you receive drops to 1/4, and this quickly leads to an extremely strong decline as you go deeper into the solar system. At the average distance of Jupiter, about 5.2 astronomical units from the sun, solar energy is only about 4% of that at Earth orbit, or only about 50 Waldie-Mertapsurid, a level so low that the light begins to become weak and is no longer enough to play the main role in the thermal balance of many systems. And when you continue farther to Neptune at a distance of about 30 astronomical units, solar energy drops below 1%, only about 1.5 Waldie-Mertapsurid, a number so small that you can almost not rely on it to maintain any thermal system. That is why deep space probes like Voyager 1 and Voyager 2, launched in 1977, could not use solar panels like satellites near Earth, because at that distance solar energy is too weak to generate enough electricity. Instead, they had to use nuclear power sources through devices called RTGs, or radioisotope thermoelectric generators, where heat generated from the decay of plutonium-238 is converted into electrical energy, a solution completely different from what you see near Earth. The interesting thing is that these RTGs not only provide electricity, but also provide a very important amount of heat to keep the systems from freezing in the extremely cold environment of deep space, because when you move far enough from the sun that external energy almost disappears, you no longer have to worry about overheating, but the entire problem shifts to the opposite direction: how to retain any amount of heat you have. And it is right here that for the first time you begin to touch what we can call the real cold of space. Not the imbalance between hot and cold like near Earth, but an environment where there is almost no significant external energy source, where every object gradually loses heat through radiation and moves closer to equilibrium with the background temperature of the universe. The Voyager spacecraft, after nearly 50 years of operation, are now at the edge of the heliosphere and entering interstellar space, where the environmental temperature is estimated at only a few Kelvin. And to continue operating, they must rely on the remaining heat from the nuclear source and the insulation systems designed in the 1970s, a testament to how far engineering has to go to fight the cold of deep space. And when you look at this, you begin to see an important shift in the way we understand cold. Because near Earth, cold is masked by the strong presence of the sun and the energy imbalance. But when you move away from that energy source, you begin to step into a region where nothing hides the true nature of the universe anymore. A place where cold is no longer a relative phenomenon, but becomes the background state, the default state that every object will approach if there is no energy source to maintain it. If you really want to get to the bottom of this issue, you have to do one thing, which is to remove all the interfering things and keep only the core. And in this case, that means imagining you move away from the sun, away from the stars, away from every local energy source, until nothing significant affects you anymore. And when you do that, you begin to touch a much deeper concept, which is the background temperature of the universe itself. This is no longer the temperature of a planet or a specific environment, but a common property of space, a number that no matter where you are, if you remove all energy sources, you will gradually approach it. And that number, measured with very high precision, is about 2.725 Kelvin, equivalent to about minus 270.45 cc, only a very small amount above absolute zero. What I find interesting here is not just the number, but how we know it, because it does not come from speculation, but from a series of very careful experiments beginning in 1965. When Arno Penzias and Robert Wilson discovered a weak microwave signal coming from every direction in the sky, something they initially thought was equipment error, but turned out to be a remnant trace of the Big Bang. Later, missions like COBE in 1989 showed that this radiation spectrum is almost perfect according to the blackbody distribution, meaning the entire universe exists in a very uniform radiation balanced state. And we measure this number with an error of only a few thousandths of a Kelvin. But the important thing I want you to keep is not the history of measurement, but its physical meaning, because this is not the temperature of a specific object, but the temperature of space itself when nothing else interferes. It is the minimum energy level that a system will approach if you leave it long enough without adding more energy. In other words, this is the final equilibrium state between every object and the surrounding radiation, from tiny dust particles to spacecraft like Voyager 1. All will exchange energy until they reach this level. And this is where everything becomes really interesting in the way physics often does. Because what you call cold in space turns out not to be a local phenomenon, not because you are in shadow or far from the sun, but a fundamental property of the universe, a legacy remaining from a very early time after the Big Bang, when the initial light was stretched with the expansion of space, gradually losing energy and dropping to the microwave level we measure today. That means the cold you encounter in deep space is not something happening to you in an active sense, but the background state that everything is heading toward. And you only really notice it when there is no longer any energy source strong enough to mask it. Near Earth, near the sun, near the stars, you always live in regions with energy higher than this background level, and therefore you never see the true cold of the universe. You only see its noisy versions, distorted by the surrounding energy sources. But when you go far enough and long enough, you begin to see something very important. Temperature does not decrease forever. It gradually approaches a limit, and that limit is about 2.725 Kelvin. This is where the concept of cold no longer resembles anything you have ever experienced on Earth, because there are no longer large fluctuations, no longer rapid changes between hot and cold, but a nearly static, uniform, and extremely low energy state. And if you go back to the title of this story, you will see that what I want you to realize is not how cold space is, but that the universe in its natural state is already almost at the coldest level possible, and everything you call warm, from sunlight to body temperature, is actually just small, temporary exceptions that exist thanks to local energy sources like stars and planets, while most of the universe exists in a state almost without heat, a state that if you remove all energy sources, everything will eventually head toward. To understand why the number about 2.725 Kelvin we just mentioned exists, you have to go back to a very interesting moment in the history of science. In 1965, when two physicists working at Bell Telephone Laboratories in New Jersey, Arno Penzias and Robert Wilson, were using a huge microwave antenna, about 6 meters high, originally designed for satellite communication, to measure weak radio signals from space, and they encountered a problem that at first glance seemed very ordinary but was extremely annoying, which was a kind of background noise that appeared in every direction they observed, a signal equivalent to a temperature of about 3 Kelvin, independent of the time of day, independent of the antenna direction, and it did not disappear even though they had carefully checked the entire system. They did everything an experimental physicist would do. They rechecked the equipment, ruled out noise from nearby New York City, readjusted the electronics, even cleaned pigeon droppings inside the antenna that they suspected might cause the strange signal. But despite all those efforts, the signal still existed, stable and impossible to remove. This led them to a very important conclusion, that the source of the signal was not in their equipment, but came from the sky itself, from every direction in space. At the same time, at Princeton University, a group of physicists led by Robert Bicker was looking for evidence of a theoretical prediction that had existed before, that if the universe began from a very hot and dense state, as in the Big Bang model, then there must remain a weak form of radiation that had been stretched and cooled over time, spreading throughout space. When the two groups contacted each other, they quickly realized that what Penzias and Wilson were measuring was not meaningless noise, but exactly the signal that cosmologists had predicted, a remnant echo from a very early period of the universe when all of space was once at thousands of degrees Kelvin before expanding and cooling over about 13.8 billion years. This discovery quickly became one of the most important pieces of evidence supporting the Big Bang model, and in 1978, Penzias and Wilson were awarded the Nobel Prize in Physics for their work, not because they found something they were looking for, but because they recognized the meaning of a signal that they initially thought was only equipment error. What makes this story special is not only the discovery itself, but the way it completely changed how we understand the universe, because it shows that space is not a meaningless cold void, but contains a thermal memory of the past, a trace of the time when the universe was once so hot that light and matter could not exist separately. And as the universe expanded, that light was stretched, lost energy, and dropped to the microwave level we measure today. This means the cold you see in space is not the original state, but the result of a cooling process that has lasted billions of years, a process in which the universe gradually lost its initial thermal energy. And when you look at the 2.7 Kelvin number this way, it is no longer a random number, but a direct sign that the universe was once much hotter, once in a state where the temperature was high enough to ionize all matter, and only when it expanded and cooled did atoms form, stars appear, and finally planets like Earth. And this brings us to a deeper realization about the cold we are talking about, because it is not a simple condition of the current environment, but the result of the entire thermal history of the universe, a history that you can hear in the form of a faint microwave signal coming from every direction in the sky, a continuous echo of the Big Bang that still exists to this day, and that very echo defines what we call the background temperature of space. What makes that discovery truly profound is that it not only tells you how cold the current universe is, but also tells you a 13.8 billion year story about how it has cooled, because according to the Big Bang model, the early universe was not cold at all, but extremely hot and dense, to the point that in the first few 100,000 years, the temperature was high enough that electrons and protons could not combine into atoms, and light was trapped in a dense sea of plasma. But when the universe began to expand, a process we know from Edwin Hubble's observations in the late 1920s, space itself stretched out, and as space expanded, everything inside it was stretched along with it, including light. When the wavelength of light is stretched, its energy decreases in inverse relation to the wavelength, and this means the light gradually cools down over time, from high energy light in the visible and ultraviolet range, gradually shifting to the infrared range, and finally to microwaves that we measure today in the form of cosmic background radiation. This process is not a one-time event, but a continuous process that has lasted throughout the history of the universe, where with every second that passes, space expands a little more, the wavelength stretches a little more, and the energy decreases a little more, and the result of this accumulation over billions of years is precisely the background temperature of about 2.725 Kelvin that we just mentioned. This also means that the cold you see in space is not a fixed state, but a state that is progressing, a cooling process that is still continuing to this day. Observations from missions like Planck show that the universe is still expanding, and even expanding faster due to the influence of dark energy, when astronomers observe the acceleration in the expansion rate of the universe. And this means that in the future, the wavelength of light will continue to be stretched further, energy will continue to decrease, and the background temperature will continue to approach absolute zero more closely. If you imagine the universe as a giant thermodynamic system, then it is heading in a very clear direction, from the initial hot and high energy state, gradually toward a colder, more dilute and lower energy state, a process that in physics is sometimes called heat death, where all temperature differences gradually disappear and there is no more free energy to do work. This does not happen tomorrow or in a few million years, but on a time scale of billions to trillions of years. But the direction is very clear. The universe is gradually cooling, and the cold you see today is just a snapshot in that process. And when you look at it this way, you begin to see that the cold of space is not something random or local, but the inevitable result of how the universe operates, a direct consequence of space expanding and energy being dispersed. This also helps you understand why heat sources like stars and galaxies become so important, because they are the rare places where energy is still concentrated enough to create high temperatures, while most of the universe has drifted toward a much colder state. And when you put all of this together, you begin to see a more complete picture. The cold of space is not a surface feature, but a profound trend, a direction that the entire universe is pursuing, where temperature continues to decrease, energy continues to disperse, and everything gradually moves closer to a state where there is nothing left to lose. A state that, from the perspective of physics, is almost the endpoint of all thermal processes. And what makes this picture truly thought-provoking is that when you look at where heat still exists, you realize that it is not the rule, but the exception, because what we call warm in the universe actually only appears in very special places like stars. For example, the sun, with a surface temperature of about 5,788 Kelvin, or stellar cores that can reach millions of Kelvin, due to nuclear fusion reactions. But these regions occupy only an extremely small fraction of the total volume of the universe. When you leave stellar systems and look into the space between galaxies, you will see an environment that is almost empty, with a density of only a few atoms per cubic meter in the intergalactic medium, billions of times lower than the air on Earth. And in those regions there is no significant energy source to maintain heat. So the temperature gradually approaches the background level of only a few Kelvin that we have mentioned. Modern astronomical observations show that most of the universe, by volume, is not the bright regions you see in galaxy images, but dark, cold, and almost matterless space where there are no stars, no planets, and no concentrated energy sources at all. Even in a galaxy like the Milky Way, which contains about 100 to 400 billion stars, the distance between stars is still very large, often light years, and most of the space between them remains in a cold and dilute state, with temperatures of only a few tens of Kelvin in gas clouds, and dropping close to the background level in emptier regions. This means that when you look at the universe on a large scale, the places with high temperatures like stars and planets are just tiny hot spots scattered in an almost endless cold ocean. And this is where your intuition is once again reversed, because on Earth you are used to heat being the normal state. You live in an environment with a stable average temperature of about 15 Celsius, with relatively small fluctuations. But in the universe, it is completely the opposite. The default state is cold, and heat only appears when there are special conditions to concentrate energy, like gravity gathering matter enough to trigger nuclear fusion in a star's core. And this is not just an interesting detail. It is a fundamental realization about how the universe operates, because it shows that what you call heat is actually a rare state, a deviation from the natural equilibrium state of the universe. When you place an object in space and leave it there long enough without any additional energy source, it will not maintain its current temperature, but will gradually lose energy and approach the background temperature. And this applies to everything, from a tiny dust particle to a spacecraft, and even large celestial bodies, if they have no internal energy source. And when you look at it this way, you begin to see that warm places like Earth, where water exists in liquid form and temperature is stable within the range where life can exist, are not the norm, but the exception, an exception created by a very specific and rare chain of conditions. And this leads us to an important conclusion that you may have already begun to sense from the previous parts, which is that the cold of space does not need to be explained as a special phenomenon, but warmth itself is what needs to be explained. Because if you remove all local energy sources, if you look at the universe in its natural state, you will see that almost everywhere is cold, and what we experience on Earth is only a very small part of a much larger picture, where energy dispersion and low temperature are the rule, while high temperature is only temporary bright spots in a system that is gradually cooling. When looking from a physics perspective, that is Earth, because if heat is truly the exception in the universe, then the planet you are standing on is one of the clearest exceptions, a rare system where energy is retained long enough and stably enough to create the environment we call normal. Earth is at an average distance of about 150 million kilometers, or 1 astronomical unit, from the Sun, a position that lies within what astronomers call the habitable zone, where the energy received is not too great to evaporate all the water like on Venus, and not too small to cause water to freeze completely like on Mars. And this position alone is already a very specific condition. But position is not everything, because if you remove Earth's atmosphere, the average surface temperature would not be about 15 Celsius as it is now, but would drop to about -18 Celsius. And this has been clearly calculated in climate models, meaning most of the planet's surface would freeze, and liquid water, a vital component for life, would not be able to exist stably. Earth's atmosphere, with its main composition of nitrogen and oxygen, along with a small amount of greenhouse gases like CO2 and water vapor, creates a heat-trapping effect of about plus 33 Celsius, retaining some of the infrared radiation emitted from the surface and slowing the process of heat loss into space, a mechanism you can understand as a giant thermal blanket surrounding the planet. At the same time, Earth has another protective factor that you cannot see directly, which is the magnetic field generated by the motion of the molten iron core inside the planet. And this magnetic field creates a shield against the solar wind, the stream of high-energy particles continuously emitted from the sun at speeds of hundreds of kilometers per second. Without this protection, the atmosphere could be gradually eroded over time, similar to what happened to Mars over billions of years, when it lost most of its atmosphere and became the cold and dry planet we see today. And when you combine all these factors, the right distance, an atmosphere thick enough to retain heat, but not too thick to cause a runaway greenhouse effect like on Venus, a magnetic field strong enough to protect the atmosphere, and in addition the presence of liquid water and a stable energy cycle from the sun, you begin to see that the environment you are living in is not the default, but the result of a very specific and rare chain of conditions. Observations of exoplanets in recent decades, from missions like Kepler or TESS, show that there are billions of planets in the galaxy, but only a small fraction of them lie in the habitable zone. And even among those, not every planet has a suitable atmosphere or a strong enough magnetic field to maintain thermal stability. This means that what you experience every day, air at about 20 cc, water in liquid form, relatively slow and predictable temperature changes, is actually a very special state in a universe where most of it exists in a cold and dilute state. And when you look at Earth from this perspective, you begin to see that it is not just our home, but an extremely sophisticated energy balance system, where every factor must work together to maintain temperature within a very narrow range, enough for life to exist. If you change one of these factors, if the distance to the sun is a little greater, if the atmosphere is thinner, if the magnetic field weakens, or if the energy source from the sun changes significantly, the entire system could fall out of this balance and head toward the default state of the universe, which is cold. And this is the point where you begin to see clearly what we have been building from the beginning, that warmth is not something obvious, but a special condition that must be continuously maintained. And without those mechanisms, Earth would no longer be the familiar place you know, but would become part of the cold ocean in which most of the universe exists. When you look deeper into all the conditions that have made Earth such a warm exception in a cold universe, you begin to realize that this is not the result of a single factor, but the combination of many conditions, fine-tuned with astonishing precision, and if just one of them changes significantly, the entire system can collapse. First is the distance to the sun, about 150 million kilometers, or 1 astronomical unit, placing Earth in the region that scientists call the Goldilocks zone, where the received energy is just right for water to exist in liquid form for long periods. Not too hot like on Venus with surface temperatures over 460 cc's due to runaway greenhouse effect, and not too cold like on Mars with an average temperature of about minus 60 Celsius due to an atmosphere that is too thin. But distance is only part of the story, because even if you place a planet at exactly that position, if its mass is not large enough, gravity will not be able to retain an atmosphere, and then all the thermal energy received will quickly be lost into space, similar to what has happened to Mars over billions of years of its evolution. Earth, with a mass of about 5.97 × 10 to the 24 kgs, is large enough to hold a thick and stable atmosphere layer, but not so large that it retains light gases like hydrogen and helium at high levels like the gas giant planets. And this creates a very delicate balance. Next is the atmospheric composition, which not only needs to exist, but also to remain stable for billions of years. With the presence of gases like CO2 and water vapor, sufficient to create a greenhouse effect that retains heat by about plus 33 cc, but not so much as to cause a runaway greenhouse like on Venus. And this requires a complex geochemical cycle, such as the carbon silicate cycle, to regulate the amount of CO2 in the atmosphere over time. In addition, Earth's magnetic field, generated by the motion of the liquid iron core, acts as a shield against the solar wind, helping to protect the atmosphere from being blown away, a factor that Mars lost when its core cooled gradually and the magnetic field weakened. When you put all these factors together, you begin to see that each condition is not only important individually, but also interdependent, forming a complex interconnected system where if just one link is broken, the entire thermal balance can be lost. And this is reinforced by observations of exoplanets in recent decades, from missions like Kepler and TESS, showing that although there are billions of planets in the Milky Way, the number of planets that converge on enough conditions to maintain a stable environment like Earth is very small. This does not mean Earth is unique, but it shows that the conditions necessary to create a stable, warm environment in a cold universe are not something that happens easily. And when you look at the issue this way, you begin to see that the existence of a planet like Earth is not something obvious, but the result of a chain of conditions fine-tuned with high precision, where each factor must lie within a very narrow range to maintain energy balance. This also returns to the larger idea we have been building, that warmth is not the default state of the universe, but a rare state that needs to be maintained by many factors at once. And if any one of those factors changes significantly, the system will gradually slide toward a colder state, the state in which most of the universe exists. Looking from that perspective, when you return to the original question about how dangerous space is, you begin to realize that cold is not the main enemy as you once thought, because what truly threatens life in space is a set of physical factors that occur almost immediately when you lose the protection of Earth's environment. And the first of those factors is vacuum. When the surrounding pressure drops to nearly zero, the human body is no longer in equilibrium with the environment, and the fluids in the body begin to react according to the basic laws of thermodynamics. Water in soft tissues and in the blood can begin to evaporate at body temperature, a phenomenon called ebulism, which has been recorded in NASA experiments from the 1960s, where scientists observed swelling of tissues due to dissolved gases escaping as pressure decreased. At the same time, the lack of oxygen causes the brain to quickly fall into an energy deficit state, and as we said before, a person can lose consciousness in only about 10 to 15 seconds before any effects of cold become significant. But even if you could somehow survive those first seconds, another danger is always present, which is high energy radiation from the sun and from deep space, including ultraviolet rays, X-rays, and high energy particles such as protons and heavy ions, things that on Earth are largely blocked by the atmosphere and magnetic field. But in space they can impact the body directly, damaging DNA, increasing the risk of mutations and cancer, and in cases of long enough or strong enough exposure, can cause acute radiation syndrome. NASA studies of astronauts on the International Space Station show that even in low Earth orbit, where there is still some protection from Earth's magnetic field, the radiation exposure level is still much higher than on the ground, and this only increases as you move away from Earth. At the same time, the thermal balance problem we have discussed from the beginning still continues to exist, because the body and equipment must not only face heat loss, but also face extreme temperature differences between light and shadow, where one part can be heated by solar radiation, while the other loses heat into deep space. And without precise thermal control systems, this can lead to equipment failure or thermal stress on the body. All these factors occur at the same time, not in sequence, giving you no time to adapt, and this makes space an extremely harsh environment, not because of a single factor, but because of the combination of many physical factors working simultaneously. And when you look at the overall picture, you begin to see that cold is only a small part of the story, a manifestation of energy not being retained, rather than the main cause of danger. This also explains why life support systems in spacecraft and spacesuits do not only focus on maintaining temperature, but must handle pressure, supply oxygen, protect against radiation, and maintain thermal balance all at once, because all these factors are equally important in keeping humans alive. And this is the point where you begin to see clearly that the question, how cold is space, is actually only a very small part of a much larger question, which is what happens when you leave the environment that your body evolved to survive in. And the answer does not lie in a temperature number, but in the entire system of physical laws you face when you no longer have Earth's protection. And it is precisely this that makes space frightening in a much more profound way than the simple image of cold, because it does not just take away your heat, it takes away all the conditions you need to exist and leaves you in an environment where every mistake is amplified by the unforgiving laws of physics. When everything we have gone through comes together, from the way heat actually transfers, the energy imbalance between light and shadow, the dominant role of the sun, to the background temperature of only about 2.7 Kelvin of the entire universe, you begin to see a picture that is not only clearer, but also much more profound. And that is where the truth becomes truly frightening. Not because it is dramatic in the movie style, but because it is completely contrary to the way you have been used to thinking. Space is not a place that is freezing cold, in the sense that something is actively making you freeze solid. It is not an environment full of cold attacking you, but on the contrary, it is almost empty of anything. And it is precisely that emptiness that is important, because what you call cold is actually only the absence of thermal energy, not the presence of any entity. On Earth, you always live in an environment where energy is retained, distributed and reused continuously. The atmosphere holds heat, the oceans store energy, convection currents transport heat throughout the planet, and so you are used to heat being the default state, with cold only a temporary drop. But in the universe, everything is completely reversed. The default state is lack of energy, is cold, and heat only appears when there are very special conditions to concentrate energy again, as in the cores of stars or on the surfaces of rare planets like Earth. When you look at the real scale of the universe, this becomes even clearer, because most of its volume does not lie in the bright galaxies you see in astronomical images, but in the space between them, where matter density is extremely low, where there are no significant energy sources, and where every object, if left long enough, will gradually lose energy and approach equilibrium with the background temperature of a few Kelvin. But places with heat, like stars with millions of Kelvin in their cores, or thousands of Kelvin on their surfaces, are actually just tiny bright spots, temporary exceptions in a system whose overall trend is to cool and disperse energy. And this is where the idea of warmth begins to change completely, because the warmth you feel every day, gentle sunlight on your skin, air at about 20 cc, water in liquid form, all of that is not something obvious, but the result of an extremely specific and rare chain of conditions, a fragile balance between energy received and energy lost. And if just one factor in that chain is broken, the system will quickly slide toward the default state of the universe, which is cold. This has a very profound consequence for life, because all forms of life that we know depend on the existence of free energy, on temperature differences to carry out chemical reactions, to maintain structure, to metabolize. And in an environment where there is almost no such difference, where everything gradually moves toward a low thermal equilibrium state, the ability to sustain those processes becomes extremely limited. This does not mean life cannot exist elsewhere, but it shows that the conditions for it to exist are not common, but rare, because you need a stable energy source, a mechanism to retain heat, and a system that can maintain energy balance for a long time. And when you look back at the entire story from the beginning to here, you begin to see that the original question, how cold is space, is actually the wrong way to ask, because it makes you think that cold is the main problem, while in reality, the deeper issue is the near complete absence of energy, a state in which nothing is provided for you, nothing to sustain you, and if you do not bring your own energy, you will gradually lose everything. It is precisely this that makes space frightening in a very different way, not because it is aggressive, but because it is completely indifferent. It does nothing, and it is precisely that doing nothing, the absence of all familiar mechanisms, that forces every system to struggle on its own to survive. When you return to your familiar world, after looking through the lens of physics and cosmology, you begin to see everything around you is no longer normal as before, because the things you once took for granted are actually extremely special. Liquid water, for example, the thing you see every day in a glass of water, in rain, in the oceans, actually only exists stably within a very narrow range of temperature and pressure. And if you place Earth a little closer to the sun, it would evaporate. A little farther, it would freeze. And that means the existence of liquid water is not something common in the universe, but the result of a very specific balance. The air you are breathing, a stable mixture of nitrogen, oxygen, and other gases, not only provides oxygen for life, but also acts as a thermal buffer, absorbing and distributing energy, making temperature changes happen gradually instead of suddenly. And if you remove this atmospheric layer, you will immediately face the extreme thermal fluctuations we have seen on the moon. Even the temperature you feel, about 20 cc on a pleasant day, is not something default, but the result of the balance between energy coming from the sun, the greenhouse effect retaining some heat, and the planet's ability to radiate heat into space. A sophisticated system that if thrown off balance, the entire environment will change. When you look beyond Earth, you see that these conditions are not common at all. On Venus, the surface temperature is high enough to melt lead. The thick atmosphere holds heat to the point where there is no stable balance, while on Mars the atmosphere is too thin to retain heat, causing strong temperature swings and liquid water unable to exist long-term on the surface. And if you go even farther, outside the solar system, most planets and celestial bodies lie in deep cold, without enough energy to maintain any stable environment like Earth. Observations of exoplanets in recent decades, from missions like Kepler, have shown that although there are billions of planets in the Milky Way, planets that converge on enough conditions to have liquid water, stable atmosphere, and suitable temperature are very rare, and even when they exist, they are often at very great distances, in conditions we cannot yet reach. This means the environment you are living in, the air you breathe, the water you drink, the temperature you find comfortable, all of that is not the standard of the universe, but an exception created by a chain of rare conditions coexisting. And when you realize that, you begin to see that your daily experiences, warm sunlight, gentle breeze, the slow change of temperature between day and night, are not something obvious, but the result of an extremely sophisticated energy balance system that is continuously operating around you. The interesting thing is that you almost never realize this, because you evolved to live in exactly that environment. All your senses, all your intuitions, are built on the assumption that this is the normal state. But when you place it in the context of the entire universe, you begin to see that normal is actually a very special case. And it is precisely this difference that changes the way you look at everything. Because instead of considering the cold of space strange, you begin to see that the warmth of Earth is what needs to be explained. And when you look at your familiar world that way, you not only see it differently scientifically, but also perceptually, because you realize that you are living in a rare thermal respite amid a cold universe, a place where energy is retained long enough to create life, to create motion, to create what you call everyday life. And this is not only a scientific truth, but a new perspective on your own existence, that the simplest things, like a glass of water, a breath of air, or a warm day, are actually the rarest things in this vast universe. After peeling back each layer of intuition and replacing it with what physics actually says, you begin to see that the story was never really about cold, in the sense you thought at the beginning, but about how we misunderstood the nature of the universe from the very start. Cold is not a special phenomenon that needs to be explained. It is the default state, the background state that everything heads toward when there is no energy source to maintain it. A state you have seen clearly through the background temperature of about 2.7 Kelvin, through the space between galaxies, through the dark regions where energy almost does not exist. In contrast, warmth, the thing you experience every day and consider normal, is the rare thing, a deviation from the natural equilibrium state, something that only appears when very specific conditions converge, when energy is concentrated strongly enough to resist the universe's tendency to disperse. You can see this at every level, from a star like the sun burning hydrogen at temperatures of millions of Kelvin to produce light and heat, to a planet like Earth retaining some of that energy thanks to its atmosphere, magnetic field, and proper distance. And if you remove any factor in that chain, the system will quickly lose its warmth and head toward a colder state. This shows that the universe is not designed to sustain life or warmth. It simply follows the laws of physics, where energy always tends to disperse, where every system progresses toward a lower energy state over time. And in that, what is remarkable is that when you look back at how we usually imagine space, you will see a complete reversal. We often ask, how cold is space? As if cold is the standout feature that needs to be emphasized. But the better question, the deeper question, is why are there places that are not cold? Because if you look at most of the universe, the default answer is always cold, almost without energy, almost with nothing happening. And that brings you to a very different realization about your place in the universe, that you are not living in a typical environment, but existing in a rare exception, a region of space where energy is retained long enough to create stability, to create structure, and ultimately to create life. And it is precisely that which changes the way you look at everything around you, because the things you once took for granted, air to breathe, water to drink, comfortable temperature, sunlight that is just warm enough, all of those now appear as very special conditions. Conditions that if you leave them even a little, you will immediately see them disappear. Space does not need to do anything to become dangerous. It only needs to exist as it is. An environment that provides no energy, no protection, no regulation. And in that environment, every system must maintain its own energy balance or fail. And when you understand this, you begin to see that what is frightening in the title does not lie in the low temperature number, does not lie in space being able to approach absolute zero, but lies in the truth that that state is the natural state of the universe, while the warmth you are experiencing is only a temporary exception. That does not make the universe hostile, in the sense of having intention, but it makes it indifferent, an environment where nothing is designed to support you, where every condition necessary for life must be created and maintained within a very narrow range. And this is where the story comes back to you, not as an observer of the universe from afar, but as part of it, because you are existing in a region that by every physical standard should not be common, a region where energy is balanced delicately between incoming and outgoing, a region where life not only exists but thrives. What is astonishing is not how cold space is, but the fact that you are existing in a place that is not cold, a place where conditions have converged enough to create warmth, stability, and ultimately the awareness for you to ask this question in the first place. And when you look outward, into the dark and cold space we have talked about, you do not just see a harsh environment, but you see the context that highlights the special nature of the very place you are standing. Because in a universe whose natural tendency is to cool, to lose energy, to head toward cold equilibrium, the existence of a warm world like Earth is not just a small detail, but an astonishing exception, a rare bright spot in a vast system where most of it is quietly heading toward a cold state. And perhaps, when you understand that, you will no longer ask how cold is space, but will begin to ask a different, much deeper question, which is why is there anywhere that is not cold in a universe like this? If you want to continue exploring scientific truths that make you look back at the entire universe in a different way, please subscribe to the channel so you do not miss the next stories. See you in the next video, where we will continue to dive deeper into things that seem familiar, but are completely not what you think.